Question 5 from the practice final reads that we have a uniform magnetic and electric field in some region of space. So we have the magnetic field is B naught times Z hat, and the electric field is E naught times Y hat. So we have our X, Y, Z plane like so, and we have the applied external fields that are B and E like this. We have an isosceles triangle that we can say has these two sides that are equal are of distance or length C, the base is of length B, and of course we'll have some sort of height of this triangle, call that maybe H. And then we have a current flowing around this triangle. So we have the arrows of the direction here, the current flows around the triangle in this manner, and that current has a magnitude of I. The question asks, we want to find the torque N on this triangle. So the torque that occurs on this triangle due to these external fields. We can recall that the torque N, it's a vector, is equal to the magnetic dipole moment crossed with the magnetic field. So again, M is the magnetic dipole moment, small m, and this formula comes from section 6.1.2 in your textbook, and it's equation 6.1. So it's the very first section of chapter 6, recall. Excuse me. So the magnetic dipole moment, M, that's what we want to find because we're given B in the problem. So we know that M is equal to I times A. And this is equation 5.8. 6 in Griffiths. And what this formula says from chapter 5 is that our magnetic dipole moment is formed by some current I, the current that's flowing around the triangle in this case, times some sort of vector area. So A is the vector area of our triangle. Now it's kind of weird to think about a vector area, but what this means is that we essentially have the area of the triangle, which we know that the area of a triangle is simply 1/2 times the height times the base, width or length. So in this case, it's B, and the height is just H. And this is our area, and the area vector comes in from the fact that the current is flowing around the triangle, and we use our right-hand rule to determine the direction of this vector. So if we're curling around with the current I, we put our fingers curling around the direction of the current, and our thumb points in the direction of our area vector. So in this case, if we're curling around like so, our thumb is pointing in the negative x hat direction. So it has a negative x hat is the unit vector. So we can find our area is simply 1/2 times the height times the width, and the height in this case, if we look at H is simply the third side of our right angle triangle here. So we can say that this is just the square root of c squared times, minus b over 2 squared due to Pythagoras. This is just this distance here, h, is just the hypotenuse squared minus the width of this side, which is just b over 2 squared. Square rooted is equal to h. That's what h is. You can check that at home. And then this is in the negative x hat direction. So for this problem, we just need to find what is m to begin with. M is dependent on A. We don't know A, but we can find it using the area of this triangle in the negative x hat direction. That's the vector component. And then M is simply this area times I. So we have I times A, which is equal to IB over 2. IB over 2 with the negative from the x hat, and then the square root of c squared minus b squared over 4 x hat. So that's M. And that's what I have in my notes here. Perfect. So now moving forward, we now want to look and find what is N. So N is given by M cross B. So if we want to take this magnetic dipole moment and cross it with our magnetic field, so we have negative I B over 2, the square root of c squared minus b squared over 4 in x hat, and this is going to be crossed with b naught times z hat. Of course, all the constants we can pull out right away, and we're looking at for the cross product is simply negative x hat crossed with z hat, which is just equal to y hat. That's just the standard x, y, z cross product, where we have this has to be negative z hat, or say negative x hat crossed with z hat to give a positive y hat. We can do all of this through, and we get that N is equal to all of the constants, so I times b naught times small b, which is the width of the triangle, times over 2, and the square root of c squared minus b squared over 4. And the direction is simply negative x hat cross z hat, which is positive y hat. And we look at this, b naught I b over 2, and then square root and y hat. Perfect. So again, for this problem, we initially recall that the torque on the system is on this triangle is given by the magnetic dipole moment of the triangle crossed with the magnetic field that has been applied, which is b naught times z hat. This is equation 6.1 in Griffiths, so I strongly recommend that you read that section, chapter 6, which is the magnetic fields in matter. And we know that the magnetic dipole moment is given by the current I multiplied by the area vector A, equation 5.86 in Griffiths. And the area is given by 1/2 h times b, which is just the area of the triangle. The vector again comes from the fact that we curl around with our fingers in I, and our right hand rule gives us the thumb pointing in the negative x hat direction. This is the direction vector of our area. We can find our magnetic moment from that, magnetic dipole moment, and then again plugging into n to find our final torque. We end up with the cross product only depending on the unit vectors. Negative x hat crossed with z hat gives us a positive y hat direction, and we end up with the total torque on the system.